Hello and welcome to Physics 1401. Today I'm going to talk about motion with constant acceleration. An example of a motion along a line, one-dimensional motion with constant acceleration is free fall. When you drop an object, once it leaves your hand, the only force acting on it is gravity, and within certain distances that doesn't change. The force of gravity doesn't change. Therefore, you have a constant force, therefore a constant acceleration on the object. That's one example. Well, there may be other approximations when you're driving. You may gradually increase your speed, and then it may be considered or approximated to constant acceleration as well. So it's pretty general, and we're going to start with deriving equations of kinematics in the case of constant acceleration. And we're going to generalize free fall to projectile motion. We may not simply drop an object, but you can throw it like throwing a ball. It may follow a parabolic path. That is also governed by equations of constant acceleration. And once we get those out of the way, we can go back to solving problems using Newton's second law again. All right. So let's start with the definition of acceleration. Let's remember. So recall that acceleration had to do with the change in the velocity. So the change in the velocity, which we denote by the Greek letter delta, right? So delta V. In general, V is of course a vector, so I put the arrow there. So this has final and initial values, which we denote with the letter F for final and I for initial. Now let's just focus in one dimension, okay? So let's get rid of the other two coordinates and let's just stick with x, for instance. So we're talking about delta Vx. Okay, I'm just using the x component, and this is V final x minus V initial x. Okay, x is whatever direction the object is moving. If it's free fall, your x is the vertical direction. If you're driving on a highway, x is that straight road. Okay, so we're gonna consider a curved motion later. Even if the motion is not vertical or horizontal, let's say something sliding along an inclined plane. Okay, there's a hill, and then there's snow here, and then there's a slid. It's just sliding this way. Okay, now we are used to defining x and y like this, but you don't have to. You can rotate it, right? You can rotate your frame so that this can become your x, and you may not even need y anymore because nothing is happening in the y direction. Okay, so that's still one-dimensional motion. All right. Well, there will be cases where one dimension will not be enough, and that's when you throw a baseball, right? It follows a parabolic path, a curve like this when you throw a ball. Well, yes, in that case, it's not enough to use x. We have to use both x and y, two dimensions. So let's start with one dimension though. So we get rid of the arrow, we just use the component. I keep the index x here, following the book. You don't have to, but it's a good reminder that we're working with actually vectors in general. So delta Vx is the change in the velocity. V final x minus V initial x. And the convention is you always write the final velocity first and subtract the old one, or the initial velocity, from that. Okay, it's just convention. So that that's general actually. You can use it for delta x, same idea, x final minus x initial, right? So V changes. not because its direction changes, but its magnitude changes, and that counts as acceleration. You may have constant speed, but changing direction. That also counts as accelerated motion, but we're not doing it right now because we're confining ourselves to one-dimensional motion. Okay, so this happens in some time interval, which you can call delta t. Again, that's the final time minus initial time. Your clock may show 6 minutes past 1 when you start your car, and then when you go to the store, it's 30 minutes past 1, which will be t final. Okay, so you subtract that and you find your time interval. That's perfectly fine, but it's also customary to take the initial time to be 0. Okay, why? Because you get rid of an extra number there. Like if you start your stopwatch when you start your car, ti is 0, right? So sometimes, let's say, we just take ti to be 0, then there's no need to call tf. Instead of tf, just use t, and delta t is t. Okay, so keep that in mind. That's very common. What do we do with this delta t? Well, we divide delta Vx by it. Delta Vx divided by this delta t, and we call this the x component of the acceleration, the average acceleration. So a average x. Okay. But today we're going to focus on constant acceleration. So what is constant acceleration? That's when the value of the instantaneous acceleration is equal to the average acceleration. So let's use a graph. Let the horizontal axis be t. Let the vertical axis be this velocity in the x direction. Now, if you don't mind, I'm going to switch to this ti equal to 0 approach. So I'm here when t is equal to 0, which means my initial velocity is this, vi x. And a time later, a certain t time later, let's say my velocity increased to a value which we call v final x. Alright? So these are the initial and final values of the velocity. How do you go from that point to the other point? Okay, there are a couple of ways. You can go with a straight line, or you can pick a different path, or something like this, or many other possibilities you can imagine. Alright? As long as you're not going back in time, and as long as you don't have 2 or more velocities at a given time. Okay? I mean, this has to be function, right? But which one are we talking about today? Today we're talking about constant acceleration, and that would be the straight line in the middle. Okay, this one, the middle. Now the middle one has a constant slope, and that slope is actually nothing but the average acceleration I just defined on the left. All right. If you consider the slope here, what do? You have the rise over run, right? This is delta v x, and this is delta t. So delta vx over delta t is nothing but the slope of the straight line joining these 2 points. Now what about the other two? You can find the slope of the tangent to one of these curves at a given time. Let's say right here, you can draw a tangent line, tangent, And you can find the slope of that blue line. And in this case, actually, that may be even equal to the average acceleration. But that depends on the time you pick, right? At a later time, for instance, right here, if you consider the tangent line here, well, the second line obviously has a smaller slope, right? Less slope. So the slope changes when time elapses. This means the acceleration at that instant changes, all right? So the instantaneous acceleration, which we defined in the previous lectures as the limiting value, limit when delta t goes to 0 of this quantity, delta Vx over delta t, then that's nothing but the slope of the tangent at that point, at that t point. So, if that slope changes, we're not talking about constant acceleration, all right? So constant means instantaneous acceleration is equal to the average acceleration. And there's only really one way to go from one point to another in the velocity time graph, and that's through straight lines. Okay? It can be a positive slope, which means velocity is increasing, or it could be a negative slope, which means velocity is decreasing, or you may have a horizontal line, which means the object is not actually accelerating at all. Acceleration is 0, but that's within the boundaries of what we're doing, okay? I mean, 0 acceleration is still constant, right? 0 is a constant, if you will. Okay, so be very careful while interpreting this velocity time graphs. For instance, the difference between, let's say, this one I just drew and a 0v. Okay, I mean both actually point at 0 acceleration, but the white line gives you a constant speed, right? The speed doesn't change, but the red line means there's no speed at all. The object is not actually moving, it's at rest. All right, so what to do with it? Let's take that equation, the average acceleration definition. I'm going to rewrite it right here. And I'm going to drop the letters AV, because we know that average is A in this case. So just A is equal to delta Vx, which is V final x minus V initial x divided by delta t, and I'm going to use the convention I just suggested. Let's say we start our stopwatch when we start moving, or let's say ti is 0 simply, so this is just t. Okay, by the way, it's sometimes I write the v final x, sometimes I write vx final. What I really mean is v final x, okay? So if I ever write this, it's nothing new. I just it's just a typo, okay? So be careful. I mean, it's not wrong, but I just want to stick with the notation book uses. So write the letters I and F before X. Okay, so this is what we're talking about. A is VFX minus VIX. I'm going to solve this for the final velocity. V final x. Okay, how do I do that? I multiply both sides by t first, and then add Vix to both sides. So I will get V final x is equal to V initial x plus A times t. Okay, a very typical equation. We call it the equation of a line, a straight line. You may remember this from analytical geometry. Okay, now of course when you use the coordinates x and y and you define, you come up with an equation that's going to represent a straight line that maybe intersects the y-axis at a point here, which we call the intercept, right, b, and then the slope can be found, right, and we call it m, and then any y point along this line will be given by this mx plus b, right? I'm sure you remember this from your math classes. But this equation looks very much like what I just wrote here, v final x equation, right? So Vix is the intercept. Vix is the intercept here. And your straight line is right here, the middle line, right? And then A is the slope, which we already know. And T is your parameter, right? In the horizontal direction. So it's a straight line, the equation of a straight line. So, this can be used to find the final velocity, given the initial velocity and the value of the acceleration. You can find your velocity at any given time. Okay? Now, Vix can be 0, or Vix can be a negative number. These are all possibilities. If Vix is negative, for instance, this means the motion is along the negative x direction. Example, let's say this intercept, which is Vix, is below 0, and this is your equation for, this is your straight line for representing the final velocity, and you have a negative number here. Okay, so what's happening here? You start, when you start your stopwatch, you were already moving in the negative x direction. That's what negative velocity means. But then the magnitude of that velocity decreases, the speed decreases. You're slowing down. Okay, you're slowing down, but you're still moving in the negative x direction until you hit this point here. You hit 0. That's when you stop for an instant and immediately start moving in the positive x direction, right? Over here, the velocity values are positive. Here they were negative, and here they are positive. So your velocity changed signs because you were moving in the negative x direction, but you were slowing down, and you stop and immediately start moving in the opposite direction, increasing your speed. That's what this graph represents. Okay? But there's only one acceleration value, which is a positive. Why? Because the slope is positive. So if you just draw your acceleration time graph right below it, let's try to do it like this. This is t and a, or ax. There's only one value for it. That does not change, okay? It's a constant acceleration example. Okay, so that's how we interpret these graphs. Or v initial x could be just 0. You know, that's when you start your car and you go to the grocery store. You're just moving in the positive x direction and you're increasing your speed. And of course, a realistic scenario is you would increase your speed until, let's say, you reach 40 miles per hour. And then when you get close to the destination, you start slowing down. So a realistic graph for grocery shopping, right? Let's start with V and time. You would start from 0 and accelerate for a while until you reach desired speed, and then you maintain that speed afterwards. And when you see the store, you know, you gotta slow down, and then in the parking lot you stop, right? So that's pretty much how it looks. I mean, that's very ideal, of course. I mean, in real life, your acceleration may not be constant when you're driving. Let's say you're driving a sports car, okay? You're changing gears, and then you may feel the acceleration changing, right? Just a description of what I just said. But the point is, throughout this, the velocity was always positive. What about acceleration? Well, we have three segments. In the first segment, the acceleration was positive because you had a positive slope. But then, when you were keeping your velocity constant, acceleration was simply 0. And then you have to slow down, right? Which means acceleration is negative, okay? Or AX, if you will. And the first phase, AX was positive. That's when you were speeding up. So these are all possibilities. So this formula I just wrote here applies to only a segment in that graph, okay? It doesn't apply to the whole. So this formula here applies well to this graph because there's one acceleration there. But when you consider this one over here, you have to divide into 3 time intervals. And that equation would work in each interval with different a values. All right? So you can't apply that one equation to whole graph because acceleration is not constant throughout that big time interval. Okay, you have to look in smaller intervals. Okay, so that's how you find final velocity given initial velocity. This will be actually one of the 4 or 5 equations. Actually, 4 will be enough for today. One of the 4 equations that will be used a lot in constant acceleration kinematics. Okay, so I want to call it number 1, equation number 1. Now, what other options or what other things that I want to find? Well, what if I don't know what the acceleration is, but I know the displacement? Can I still find the final velocity? Or what if I don't know how much time elapsed? Okay, or can I find the displacement in terms of the initial velocity and acceleration? Things like this, okay? So we need more practically useful formulas, and I'm going to try to derive them, okay? So let's start with delta x, which is the displacement. Delta x, in other words, x final minus x initial. So how do you find a formula for delta x when acceleration is a constant, ax? Let's put an index here, x. We're talking about the acceleration in the x direction. Okay. Now, there are a couple of ways to do it. Now, let's remember one thing we talked about last time. That was the area under velocity time graphs. So, let this be a generic change in the velocity, but a steady change. So this is v and t here. And this is v final x, and this is v initial x. And this will be the t, okay? I said area, so if you look at the area under the velocity time graph, that is equal to the displacement, okay? You should remember this, you should remember this from previous lectures. From chapter 3, the area. Like, can we find the area? We have a trapezoid here, right? If you remember the area formula for a trapezoid, fine, just apply it. If you don't, you can still do it by dividing this into 2 parts. There's a triangle here, and right below it there is a rectangle. Okay, I hope you remember the formula for finding the area of a triangle, right? You can find these 2 separately and add them, okay? So the trapezoid is, you have a base and top and a height. You take the average of the base and height, pretty much add them and divide by 2, and multiply by the height. That's the area of a trapezoid. If you don't remember it, like I said, use the formulas for the triangle area and the rectangle area, right? So let me show you both from a trapezoid, let's say. Trapezoid area of a trapezoid, which is base plus top over 2 multiplied by the height. Okay, well, the trapezoid actually is like this. Okay, this is top here. Top. And this is a base. And height would be this. Okay, so it's like 90 degrees rotated. So in that case, that area, which we can call A1, and the rectangle will be A2, I guess. So the area A1 plus A2 is the area of a trapezoid. What is it? So let's do it with this base and top formula. So base would be the longer side, which is just V final x. And you add the top to it, which would be the VIX. Divide by 2. Alright, divide by 2 and then multiply by the height. Height would be, remember this is 90 degrees rotated, would be just T. Okay, this is the area. So that will be equal to delta x, which is x final minus x initial. Or if you don't remember this formula, you can just use this approach here, which is the sum of the triangle and the rectangle. So let's do it that way. A1 is the area of the triangle. Now you can use either T as your base or V final x minus V initial x as your base, and the other one will be the height, right? So let's use T as our base. 1/2 times the base T times the height. Height is here, and that is V final x minus V initial x. Okay, that is your A1. And A2, the area of the rectangle below it, that is T base times height times VIX. Okay, so if you add these two, you get delta x. That would be VIXT, that's A2 plus A1, 1/2 T times V final x minus V initial x. Now, is this equal to what we just found above? Yeah, actually they are equal. You can prove it easily by writing this as 2 VIXT divided by 2, okay, it's the first term, plus, now distribute T here, T V final x minus T VIX divided by 2. Now that the denominators are the same, you can combine the numerators. So 2 VIXT minus T VIX is just 1 VIXT. And you have plus V final x T divided by 2. As you can see, this is equal to this value here. So they are identical, okay, which we expected. Now at this point, I'm gonna put a box around this. It looks like a nice formula. Okay, let's call this number 2. Remember, number 1 was over here, V final x minus V initial x plus AXT. Great, we found another formula. Let's do this though. equation number 1 tells me what v final x is. Okay, so this v final x from equation number 1 is equal to vix plus ax t, right? So why don't I plug that in, that expression, okay? So I'm going to take this now and rewrite it. I'm going to replace v final x with this expression here. So delta x is equal to vixt, that's the first term, plus 1/2 t. Now instead of v final x, I write vix plus axt. And then I subtract v initial x again, that's in this line here, vix. All right, and then simplify it. Now, how do I do that? Okay, so I get rid of these, vix and vix, okay? So vixt plus 1/2. Let's take this ax, write it here. T times t is equal to t squared, okay? So this also gives me delta x. It just doesn't have the final velocity in it, only the initial velocity and acceleration, okay? So that's a formula which I can use. I'm going to call this equation number 3, okay? And these numbers are just arbitrary. You can call this one number 1 and the other one number 2, doesn't matter. But that's a very practically useful tool, okay? It's an equation. So I'm not asking you to memorize them, but you'll realize that if you soon enough, I mean, you're going to use them so much that you're going to memorize them, okay? But you don't have to. Okay, so what if we don't know how much time elapsed? Okay, can we still find the final velocity from initial velocity? Yes, as long as we know some other things like the displacement and acceleration, okay? So let's take these 3 equations, okay? Remember, this was equation number 1. We have 1, 2, 3, and let's eliminate time, okay, and see what we get, okay? Now you can use, which one? I mean, you can use, let's use 1 and 2, right? Let's use 1 and 2. Both equations have time in them. Let's get rid of time, okay? So let's take this equation, for instance. Let's rewrite it, okay? V final x plus v initial x divided by 2. Now instead of t here, I'm going to write what I would obtain from equation number 1. Now let's do that right here. If you subtract v initial x from both sides, this is what you get. And now divide both sides by a, or ax, and you get t, right? So if you do that, this is what you're going to get. V final x minus v initial x divided by ax. That's going to give you delta x, okay? So I took equation number 2. Instead of t, I just wrote this. This is equal to t from equation number 1. Good, I got rid of t. Let me simplify this equation then. Now, this is v final x plus vix times v final x minus vix. All right? What do you get when you do that? You get v final x squared minus v initial x squared. Right? That's in the numerator. In the denominator, we have 2 times ax. That's equal to delta x. So let's rearrange this. Let's multiply both sides by 2ax and then add vix squared to both sides. If you do that, you will get v final x squared is equal to v initial x squared plus 2ax times delta x. Alright, so this will be our equation number 4. Alright, so here are the 4 equations of kinematics in the case of constant acceleration. These are extremely useful. As you see, these are not totally independent from each other. At least we derived equation number 4 from 2 and 1. Okay. I mean, you could come up with the same equation by using 2 and 3 or 1 and 3. Okay, you can try that at home if you like. I mean, just play with these and see if you can get equation 4 yourself. So it's not the only way. Actually, you can even add a 5th equation if you like. For instance, consider equation number 3 here. That gives you displacement in terms of the initial velocity, the acceleration, and time. What if I don't know what the initial velocity is, but I know the final velocity? Can I come up with a way to find delta x in terms of the final velocity plus time and ax? Yes, I can, you know. To do that, instead of replacing v final x by this value here, you could replace vix by whatever you would get from the solution here, and then you would end up with delta x as a function or dependent on the final velocity. Okay, so some people would call it the 5th equation. All right, but you don't need. I mean, these are all related. So sometimes in problems you will use just one of these equations and you'll get to the answer like that. Sometimes, you know, you may use 2 of these equations. So you solve one of them and then obtain something, let's say time, and then plug that time into another equation and you get the answer. Okay, it's possible. So either 1 or 2 of these will be used in problems. Okay, so maybe I should now solve some examples. Okay, so let's use the book again and find a couple of problems to solve. And then after that, I'm going to talk about free fall and projectile motion. Okay, so at the end of the chapter, there are some problems here. Okay, and let's do number 10 here. Okay, I'm going to clean everything here, clear canvas, and then solve this problem here. Okay, let's see what it says. A car is speeding up and has an instantaneous velocity of 1 meters per second. Instantaneous velocity of 1 meters per second in the x direction. Okay. When a stopwatch reads 10 seconds. When t is 10. It has a constant acceleration of 2 meters per second square. Okay? So why don't I call this Ti and then call this Vix? Okay, so this car is traveling in this direction, which is x, positive x, and when your watch shows t equals 10 seconds, that's your instantaneous velocity, but that's going to be changing, right? Because you have a positive acceleration also, you're going to speed up. That's what they're asking here. A, what is the speed when the stopwatch reads 12 seconds? I'm going to call this V final. Okay, final doesn't mean the car stops. Okay, final means the velocity at TF. That's all it means. So what is VFX when T is T final, and that is what? 12 seconds. All right, that's part A. And part B, how far does the car move between T equals 10 seconds and 12 seconds? How far does it move? They're talking about delta x, right? Delta x. Now, they never tell us where the car was when T was 10 seconds, okay? And they're not asking us where the car will be at T equals 12 seconds. They're only asking us the difference, delta x, okay? In other words, they don't tell us where the origin is. Origin is when x is 0. We don't need to know, because our formulas have delta x, okay? Delta x is x final minus x initial. So don't worry about x initial and x final. We just need to find delta x, the displacement, that is. All right, so for part A, we need the final velocity. It's actually really simple. I think the first equation, equation number 1, is exactly what we need, right? Let's rewrite it here. V final x is equal to V initial x plus ax times t. But you've got to be careful here, okay? This t in our formulas was actually delta t. Remember I said take ti equal to 0 and then tf, simply call it t. So we got to be very careful here. So this t here will be 12 minus 10. Which is 2 seconds. Okay? It's a time interval, actually. That is a time interval. Delta t. So, the initial x is 1 plus ax, 2 meters per second square, times t. T is 2. All right, so 2 seconds later, when your watch shows 12 seconds, the velocity will be 2 times 2, 4 plus 1, 5 meters per seconds. Okay, so if you wish to draw a graph, it looks like this. T and Vx. Now I'm going to use those values, 10 seconds and 12 seconds. 10 and then 12. Okay, so what we have here between 10 and 12 is this. Okay, I mean, this is not drawn to scale, so I mean, it looks like it's going to cross 0, but it won't, okay? So be careful. But Vx simply increases from 1 to 5 meters per second, and that happens in just 2 seconds. Okay, that's how you would draw it using the given data. Now, actually, if you wish, for part B, you could find the area under this and you'll be done, okay? Now we can use it for confirming our answer, but let's just use the formulas we derived, okay? So part A used one of the formulas. For part B, we need delta x. So let's use one of the 2 formulas. Why do I say 2? Because we have 2. We have this one, delta x equals the average of the velocities or if you prefer, you could use the other one we derived, Vix t plus 1/2 AT squared. Okay, since these formulas are derived from each other, both should give you the same answer. So you can use whatever you like. If you didn't know the answer to part A, for instance, of course you can't use this formula. You have to use the second one. All right. But now that we solved part A, we could use that value, which is 5, right? So Vix is 1. Add Vfx to it, which is 5 meters per second. And I forgot T here. Let me just put T. All right. So this times T, which is 2 seconds. And you get 6 meters, right? If you want to use the other equation, hopefully we'll get the same answer. Let's check. Vix is 1 meters per second times 2 seconds, that's T, plus 1/2 times A, which is 2 meters per second square, times T squared. Don't forget the square. Okay, it's T squared. So this gives you 2 meters plus 2 times 2, 4 meters, which is 6 meters. Okay, so both formulas give you the same answer. What about that area method I was talking about? Area is also delta x. You can confirm this result. Okay, the area of a trapezoid, base plus top. Base is 5, top is 1, divide by 2, times the height, which is 2. 6 meters. Alright, so that's how you find it. Very basic application of these formulas. Okay, I think the tricky part in this problem was this Ti and Tf values, okay? Because I had to remember that the T in the formulas I derived stands for the time interval, okay? So if you take this formula and just plug in 10 or 12, you would get the wrong answer, okay? Don't do that. Okay, so one thing I just remembered. Okay, so I probably didn't mention this when deriving the equation, but obviously whenever you have something like this and you have two values, Vix and V final x here, and T, the average value right in the middle okay, this corresponds to V final x plus V initial x over 2, right? The average value. So that's what we're multiplying by t to get delta x. Now check this out. You have, if you continue this, now we have two triangles, right? One here and one there. And due to symmetry, these triangles have the equal area. So if you take this one and rotate it and bring it over here, it perfectly fits. So what do you have then? Then you have a big rectangle, right? And the area of that rectangle is equal to the area of the trapezoid, right? The area of the rectangle, shaded in red, is equal to the area of the trapezoid. And the area of a rectangle is simple. Base times height. So base is t, base times height. Height is this number here. And you get the answer, okay? So everything fits in this picture. Very simple, but very useful at the same time. All right. Now, speaking of graphs, you got to be careful when you have negative velocities. Remember this one here? when you start from a negative velocity, you slow down and then your speed becomes 0, and then immediately you start moving in the positive direction. Remember this? Now you can also find the areas here. Call this area 1 and then area 2. But you got to be careful when adding this up. If you add the two numbers, and I say numbers, I mean the positive values, okay, the absolute values, the actual area. When you add them up, you get the big area. That will not be equal to the displacement. That will be equal to the total distance traveled. Remember, when you find average speed, you divide total distance traveled by total time. That gives you average speed. But when you do average velocity, you divide the displacement by time interval, okay? So since you were moving in the negative direction, let me draw a picture here. So you were moving in the negative direction, you slowed down, you stopped, and then you start moving in the positive direction, okay? So suppose this was the actual path, then this corresponds to the displacement because the initial and final positions are known, right? But the actual distance traveled, if you're driving, you're burning gas, right? I mean, the distance is actually longer than delta x. The distance here, let's call it d. So this, call it d1, call this d2, and then call this distance d3. This will be the sum of the three, right? d2 plus d3. So just be careful, okay? So if you subtract a1 from a2, all right, if you do that, which would be, okay, so if you take the subtract, and then you may find the actual displacement, okay? So be careful with this, all right? Be careful when you have negative velocities. All right, so this was number 10. Let's talk about free fall. Free fall. Now the free fall is actually a term that is used to describe the motion under the constant acceleration due to gravity. Okay, gravity is the key word here. And let not the term fall fool you, because the object may be actually going upward. Okay, that doesn't look like falling. You throw a stone in the upward direction. Yeah, I mean, it's going up, it's not falling. But since the only force acting on it once it leaves your hand is gravity, that still falls under the category of free fall, okay? So you may just drop an object. Okay, what are the possibilities? One, simply drop it, which means the initial velocity is 0. Or you can throw it upward. Throw it upward. Then your initial velocity is no longer 0. And if you take up as your positive x direction, then this means Vix is also positive. Okay, you throw an object. It's going to immediately start slowing down, but Vix is positive. Or you can throw it downward. Throw it downward. In which case, Vix will be a negative number, okay, as long as you take up as positive. Now, I picked the positive direction as x. Some people like to call it y. And there's a reason for that, because we're not just going to do one-dimensional motion. When we do two-dimensional motion, like a projectile motion, you throw a baseball, and not only the horizontal but the vertical component changes. So it's customary to pick the horizontal as x and vertical as y. Okay, so let's say alternatively pick the up direction as y as usual, and then horizontal will be on the x. Okay, so this is the case when you throw an object, both coordinates change. Okay, so keeping that in mind, some people may just start with the y and forget about x when it's just up and down motion. Okay, all right, so that's not a big deal. I mean, you can call it z if you like. Z would be the third coordinate, right? So that's not a big deal really. Let me just check what the book is using. Well, the book is using y. All right, so let's stick with y then. Okay, so where is the constant acceleration here? Well, that's the acceleration due to gravity. Okay, the letter G, which we have seen before and has the numerical value of 9.8 meters per second square. Well, we saw this in a different context though. This was about gravity and weight. Remember, mg was the weight of the object. But today we're going to actually use it as an acceleration. As the unit suggests, it is actually, it has the physical dimensions of acceleration, and that's the acceleration due to gravity. That number, we can use it in our lab frame, okay, or when you're playing football, you can use that number, but keep in mind that number changes as you move away from Earth's surface. If you climb a mountain, it may change, or if you change your geographical location on Earth, okay? Even when you're sailing on open sea, you're not climbing a mountain, but you're closer to the North Pole, let's say, than equator, G changes, okay? That's because Earth's shape is not a perfect sphere, but it's elongated, okay? It's wider at the equator. But let's not worry about any of those, and let's use this number, 9.8 or 9.81 in some cases, as our numerical value for G, okay? And this will be the acceleration due to gravity. Or let's say the magnitude of the acceleration due to gravity. How do we know it is a constant number? Before Newton, actually, it was Galileo who did experiments with falling objects. Okay, so you take a pencil, all right, and then you take two pencils. You tie them together, okay, and then so one pencil here and two pencils here, and you drop them at the same time, and then see if they will hit the ground at the same time as well. Okay, that's what he was doing. So this is due to Galileo. He did the experiments. He tried dropping them directly, and then he tried rolling them along an inclined plane. Why? Because this was, easier to observe. Things fall really fast, right? You may not have accurate measurement. You may climb up a tower and then drop it from a tower, and you may have more time to see what's going on. Or you can just simply roll objects along an inclined plane where you have a better chance of observing accurately what's going on. So he had he devised ways to experiment this. But he observed that they all reached the bottom at the same time. I was talking about pencils, right? So one pencil here versus the bundle of a couple of pencils, let's say two of them together. Now we know from previous chapter that the weight here, let's say if this is mg, the weight here is 2 mg's because there are two pencils instead of one. We know that, right? So the net force on these are mg and 2 mg's. Alright, so if they reach the bottom at the same time, they must have the same acceleration regardless of their weight. So the net force is equal to mass times acceleration. Well, yeah, if you double the mass, effectively you're doubling the weight. So it's like putting a 2 here and a 2 there. Mathematically, it's still the same equation, right? I mean, you can multiply it by any number you like, which will have no effect on acceleration, right? Acceleration will always be the net force divided by mass. You increase the mass, the force increases proportionally, and you get the same acceleration. But it wasn't intuitive at the time, all right? Because from the time of the Greek philosophers, people have thought that heavier objects would fall faster, okay? Because that's what fit in their daily experiences. You take a piece of gold coin and a piece of feather, and you drop them at the same time, and the coin would fall much faster. And it wasn't really easy to see if they would really fall at the same time. That's why he did the experiments. And if you're wondering why the feather or the leaf or paper would fall later, is that, you know, a violation of physics? No, it's because of air resistance. Okay, air resists the motion. It can be because of the shape of the object. Meaning, are you dropping the coin flat or vertical? Okay, that will change the aerodynamics of it. Or simply the surface area. I mean, larger objects will fall slower because there's more resistance. Okay, the area of the object, surface area in the direction of movement, is a factor. So you can go online, go to YouTube and type BBC and vacuum experiment. So they do the feather and the coin, or I don't remember what the other object was, a heavy object, maybe like a concrete weight or something. So they go to a huge room and they suck the air out of it completely, okay, vacuum. There's no air in it, and they have a high-speed camera, and then they observe the motion of the feather and the heavy object. They fall at the same rate, and they reach the bottom at the same time. Okay, so if you remove the air, if you did this on the moon, okay, same thing, there's no air there. So, all right, so the fact that led people to believe that heavier objects fall faster was because of neglecting air, okay? I mean, air plays a role in there. If you take the air out, independent of the weight, meaning independent of the mass, all objects fall with the same rate, and that's this number. There's one thing you have to be careful though. Remember, we picked up as positive, right? That's very common, so let's take this as a positive y direction. Gravity is downward. Force is downward. If the force is downward, the vector A is also pointing downward. So A is a vector that points downward. In other words, if you use unit vectors, A will have a magnitude here, but its direction, this magnitude here, G, its direction will be negative y hat. Okay, if you remember the unit vector idea. Or simply draw an arrow that points downward. So when I use the component then, if I say AY is not 9.8, it's negative 9.8. Negative 9.8 meters per second square. Okay, that's very important. Signs are very important in physics. Positives and negatives, very important. Just like sines and cosines. I mean, you don't have the luxury of confusing them, okay? You have to know your sines and cosines very well. Sines and cosines, positives and negatives, and maybe later square root 2's and pi's if you go in study more physics, okay? I mean, you gotta know where to put those numbers. So if you pick up as your positive y direction, like most people would do, then AY is negative 9.8, okay? But G is still 9.8. So AY is negative G, because G just represents the magnitude of the acceleration, okay? Now, if you want to be different than others and then pick down as your positive y direction, that's perfectly fine. No problem, but you gotta remember to change the sign of AY. If you pick down as your positive y, because it's totally up to you where to pick your origin, how to name the axes. Do I want to call it Z or Y or X? Is it up positive or down positive? It's totally up to you, but once you pick it, just stick with it, okay? So if, in any case, if some of you are thinking, hey, I want to pick down as my positive direction, then AY will be simply G, okay? Not negative G, but G. But remember that if that's the case, throwing an object upward would mean giving it a negative initial speed. So up would be VIY negative, and down would mean VIY positive, just like the opposite of these two. Okay? Just telling you, I'm not to confuse you, but hopefully it makes sense, okay? It's up to you. Well, I'm gonna keep picking up as positive, but keep in mind, it's not the only way to do things. All right, so AY, which is negative 9.8 meters per square seconds, is our constant acceleration. So once we understand that, those four formulas we used before, they don't change. Just replace AY with this number. For instance, V final Y will be equal to V initial Y. Now this was what? AY plus AY times T, right? AY times T. Well, I'm just going to replace that AY with negative G. Okay, so I'm going to use that formula for free fall. This was equation number 1. Equation number 2, I believe, was about delta Y. So V initial Y plus V final Y divided by 2 times T. Okay, this was easy. Just the average of the velocities times the time elapsed. Okay, and there was another equation for delta Y, which is, by the way, YF minus Y initial, right, by definition. But the second equation will be VI Y T. Okay, this is the first term. And the second term goes like plus 1/2 AY T squared, right? So I'm going to take this and write it as VIY T minus 1/2 G T squared. Alright, this is the third equation. Just replacing AY's with negative G's. And finally, we had an equation without time. This was V final Y squared equal to V initial Y squared plus 2AY delta Y, or minus 2G delta Y. Okay? This is what you will get if you replace ay with negative g. This will be the fourth equation. Okay, now you can solve any free fall problem using these four equations. Either one of them or two of them, most of the time, will be enough. Okay, so let's do that. Let's solve a problem from the book again. Free fall, okay. Let's do 31. A balloonist riding in the basket of a hot air balloon that is rising vertically with a constant velocity of 10 meters per second releases a sandbag when the balloon is 40.8 meters above the ground. Okay, I want to draw a picture. So here's the ground, here's the balloon, hot air balloon. Okay, hopefully this drawing makes any sense. The hot air balloon is moving up with a constant velocity of 10 meters per second. And you drop a sandbag, okay? It says release. Release. What does release mean? I mean, if you're releasing the pencil, you're not really pushing it downward or upward, you're simply dropping it. But remember, I am in the balloon, and the balloon is going up, and before I drop the object was also moving up. Okay? So the initial velocity of the object that I'm releasing is not zero, because I'm doing it within the balloon. Alright? So this object is released here. Let's use green. When you release it, it will not go directly downward. It has an initial speed, which is the balloon speed, which is up. So once it leaves your hand, it's going to slow down while going upward and reach a maximum height, and then immediately turn and then start speeding up in the downward direction. So if I draw a picture here, it's going to follow a path like this. Alright, this is what the object will do. Of course, it's not going to move in the horizontal direction. That's just my drawing there. Okay, it's going to go up, slow down, and then come back or go downward. Alright, this point is very important. Okay, if you think that it's going to go straight downward, that's wrong. That never happens. That only happens if you drop it from a high-rise building, okay? But you have an initial velocity, which becomes the initial velocity of the object you're dropping. So, picking up as positive y, vi, v initial, y, is 10 meters per second. Okay, let's keep reading. 31. When the balloon is 40.8 meters above the ground, so this distance here is 40.8 meters. Now, of course, when the object does this motion, the balloon is still going upward. We don't care about that, but it won't be there anymore. Just focus on the object from now on. Ignoring air resistance, what is the bag's speed, the object speed, when it hits the ground? So this is V. Okay, let me use blue here. This is VI, Y, but the final velocity will be, of course, pointing downward. V final Y, VFY. So what is VFY? Okay, that's the question. What is this? All right, so let's look at the problem. We're given initial velocity and we're given some distance, some height. And they don't tell us, but we do know that this is a constant acceleration case. and the acceleration is equal to negative g. Okay, so these are the things that are known. We want to find the final velocity. What is not given here is t, time. Okay, we don't have time. So this is actually a very simple problem because there is only one equation among the four that does not have time. That's the fourth and the last equation, right? That equation did not have any time in it, and that's the one we have to use. There's no other alternative. Let's remember that equation. V final y squared is equal to V initial y squared minus 2g delta y. Okay, so that's the equation we're going to use. We just have to be careful. Careful with the signs, like we did here with VIY. I mean, we're taking the square of VI, so that you may think it may not be a big deal, but delta y, you got to be careful with delta y. All right. Now, we don't know where the origin is. You can pick an origin. You can pick the ground as the origin. You can pick the position of the sandbag when being dropped as the initial position, or I mean, sorry, the origin. Doesn't matter, because the location of the origin has nothing to do with displacement, which is delta y. Okay. This is displacement, vertical displacement. Since we picked up as positive for our y, whenever you end up at a point which is lower than your initial point, delta y will be a negative number. That's always the case. Okay? Whether you pick the ground as your origin, or a mountaintop as the origin, or the center of the earth, doesn't matter at all. Okay? You can try it with given numbers. Delta y will always be negative if up is positive and you end up with a point, lower than your initial point. Okay, so going from this initial point to this final point, delta y is a negative number. We're given the height of the balloon, so we just make it negative to find delta y. Delta y is, I mean, if you call this h, this is negative h. So delta y is negative 40.8 meters. Okay, so that's what you have to be careful with problems like these. It's not picking the equation. That was simple. There was only one equation that didn't have time. You pick that one, easy. But you got to be careful with delta y's sign. Okay, you look at the problem. Where is my initial point? Where is my final point? And which direction is my positive y direction? If you keep in those in mind, you're good. Actually, since we used negative g as our acceleration here, there's no option for picking down as positive, right? I mean, up is positive. There's no ambiguity there. Good. So all we have to do is to solve this equation. All right. So let's plug those numbers in. V final squared will be equal to V initial y squared, that is 10 meters per second squared, minus 2 times g. G is 9.8, okay? Not negative 9.8. G is always 9.8. 9.8 meters per second square. And delta y is negative 40.8 meters. So let's find this. 100 minus 2 times 9.8 times times negative 40.8. Okay, so 899. I'm going to write everything here, which probably I don't need that many, but it's okay. meters squared per second squared. Am I done? No, I'm going to take the square root of that, obviously. But when you take the square root, you will have two roots, okay? One positive and one negative. Take the square root of this. There are two answers. I mean, 29.9. Let's call it 30. But there's also a negative result. I mean, your calculator will not tell it, of course, but you have to remember. Whenever you're taking the square root of a number, you will have two roots. Negative 30 meters per second. Which one? Well, we know it's going downward, right? It's pointing downward, therefore it has to be the negative one, not the positive one. Because positive would mean up. We don't want that. All right, so that's your answer, 29.99466, which I rounded to 30. So this was question number 31. They didn't ask here, but if I wanted, I could add more parts to this problem and ask a couple of things like, see, it reaches a highest point here. Where would that be, for instance? Okay, that could be an additional question here. But before we speculate on that, let's find the, let's check the answer, 31, 30 meters per second. I think they go with speed here. Yeah, let's say the speed. Yeah, the speed is 30, of course, because speed is the absolute value of instantaneous velocity. Velocity is negative, speed is negative. Speed is positive, and velocity is negative. So I was saying, what would be the maximum height? Let's call this this is not part of the problem. I'm just asking you now. What would be the maximum height? And how would you find that? So let's say extra parts. What is h? Let's call this h, capital H. The maximum height. So this object leaves your hand with 10 meters per second up, but immediately slows down due to gravity, reaches a maximum height, and then turns around, starts speeding up in the negative y direction. It stops for an instant at the top. Right there, it stops. At the top, v is 0 momentarily. Okay, v is 0. Does it mean acceleration is 0 as well? No. Remember, this is a constant acceleration problem. Acceleration never changes. Acceleration is always 9.8 meters per second squared downward. It's the velocity that changes. You can draw a plot of Vy. Okay, so you start at 10, you slow down. Right here, when your velocity reaches 0, you're at the maximum height. And then you increase your speed in the negative direction and hit the ground, right? By the time you hit it, your velocity is what? Negative 30 meters per second. Right? But you see, there's only one slope. A constant slope, a constant negative slope for this picture here. Slope is equal to negative 9.8 meters per second square. It's just the sign of the velocity that changes. It changes from positive to negative. It decreases to 0, and then even more, you know, let's say increasing the speed in the negative direction. But there's only one slope, so A is not 0 here. A is not 0, okay, very important. Right over here, V is 0, but not A. A is still negative 9.8 meters per second square. Okay, so what do we do then? The problem was finding this H, right? Finding this H. What if we use the displacement formulas? We can extract it from the graph because we know the areas are there, or we can use our formulas. Okay, so how about this? We know the final velocity here. Let's find time. The specific time here, I'm going to call it t prime. Okay, t prime is when the object reaches maximum height. Let's find it. Find t prime, meaning time at the top. Now, initial velocity is known, final velocity is also known. Remember, v final y is equal to v initial y minus gt. That's the first formula, right? So solve this equation for t. When t is equal to t prime, that specific number, when t is equal to t prime, v final y is 0. V final y is 0. So what is t prime then? 0 is equal to v initial. I meant y here, sorry. This is y. V initial y. Let me erase this. V initial y. Okay, so v final y is 0, v initial y is 10 meters per second, minus g, which is 9 meters per second square, times t, which is t prime. Therefore, t prime is 10 divided by 9.8. Okay, let's find the exact figure. 10 divided by 9.8. 1.02. Approximately 1 second, but let's say 1.02 seconds. Okay, so after approximately 1 second that you drop it, it reaches the maximum height. All right, so in that time it travels a distance here, which is simply the area here, right? So t prime is around 1 or 1.02. So the area here is 1 times 10 divided by 2, 5 meters. Okay, so 5 meters on top of 40.8 meters. We just found that this here is around 5 meters. Okay, or 5.01, but it's 5 meters. You simply add 5 to 40.8, and that's going to give you h. So h will be 45.8 meters. Okay. So this wasn't part of the problem, but I just wanted to add it. Can you add more? Yeah, you can find, for instance, where the balloon will be when the object is at the top here. So only 1 second elapses. This means the balloon will be 10 meters above. Okay, so when the object you dropped reaches its maximum height and momentarily stops, you will be 10 minus 5 meters above that object. Okay, I mean, you can add extra parts to this problem if you like. Okay, I mean there are many possibilities. Okay, so that's free fall. All right, that's free fall. Let's check the time. Okay, it's been, where is the time? It's been 1 hour and 29 minutes, almost 1.5 hours. I'm going to stop here, and in the next video I'm going to talk about free fall in 2 dimensions, which is projectile motion. Okay, cannonball problems, or football problems, or firefighter using a water hose. That looks like a projectile too, right? So that's very similar to free fall, which is in 1 dimension. We're just going to add 2 more equations to it, basically. So we're going to have 6 equations in total. But let's keep it for another day. Okay, so till next time, goodbye.